Okay, then let's continue and have a look at the observation function, also on this kind of mesoscopic level. Again, this observation function takes the state vector where ns is the number of states, and this is obviously 5 times the number of regions as just discussed. It takes the state vector, and there's a missing, a set of parameters or a parameter vector in this parameter space theta g, and also partitions regions of interest wise. There are some more typos in the script. Can you throw me a pen, please? Thanks. That's needs an I, this needs an I, this needs an I, this needs an I, and this needs an I. Dankeschön. It also partitions region of interest wise, and in this case it actually partitions also in the input arguments. So the first observation function you can either have it look, like I wrote in the script, look at the entire state vector. You can also, because this really doesn't need the state vectors, the state variables from other regions, you can also have it look only at the first state vector. What this means, what needs to be specified for this is, of course, maybe I haven't done that really previously, is that this is a vector of 5 variables, namely the 5 states of the first region. Yeah. You can also view it as, of course, looking at the entire state vector, but then internally only considering the first 5 variables. It's gehüpft wie gesprungen. Important thing is that there are as many there are as many typos in this formula, in the script, as there are non-typos, actually. Sorry, I will correct these. This is actually one part of the script that I didn't revise too much. So this goes up to number of regions, and this goes up to number of regions then as well. So the M, you see an M in the script. M used to be the number of regions, but I at one point decided I want to make it more explicit, so call it NR. Now, what these observation functions are is they, for each regional state vector or for the entire state vector, I'm not quite sure, maybe I should decide what I like more. Now I'm using the entire state vector again. It maps the hemodynamic states, or not, but not all of them, but some of the hemodynamic states onto a single variable. So a single region-specific variable, which is the predicted MR signal. Oops. This goes to R. Yeah. So each of these, let's say if you have 4 regions of interest, each of these 4 G functions, these 4 observations functions, looks at the state variables within each region, and from these 5 state variables, it returns a scalar region-specific value, which is the predicted MR signal in high temporal resolution. And it does this by the following formula. There's a parameter V0, there's a parameter C1, there's not a parameter. It looks at the fifth state variable, so that's a hemodynamic state variable. And it looks at the fourth hemodynamic state variable in the ith region. So as you see in the script, this needs more ith or i's. And are these C constants which are given in terms of parameters. Yeah. So the most important thing, and never mind the details at this point, the most important thing is that it takes looks at the fifth state variable, which is the hemodynamic states variable in the ith regions, and at the fourth, and then are some additional parameters. One parameter includes aspects that relate to the imaging process, TE, and some other parameters. And as I say there, the intuitive meaning of these things will become clear. One reason why there is a little bit of chaos in terms of the ith notation there is that is actually not that clear. First of all, from the documentation, from the papers about DCM, it's quite hard to figure out which parameters are region-specific, which are not specific, and then the only way to figure out which parameters are actually region-specific is to look into the code, and of course this means that you have to study the code and go through all the DCM implementation in SPM to figure out which parameters are actually region specific, which are allowed to vary, and which are not allowed to vary. So in general, this is fairly badly documented in the literature. So I try to figure out most, but there's a little bit of a uncertainty on this. Once we get back to this function G, I will have a look whether I can find maybe in the newer papers on that some clearer indications which of these parameters are region specific. Some of them of course can't be region specific, like the TE, that's of course sequence specific, and other ones could potentially be region specific. I think this is kind of the resting state ratio between deoxygenated and oxygenated hemoglobin. Of course, this can be potentially region specific, but of course you can also make the assumption that this is the same for all regions and then not let it vary. So that's even less clear whether it's region specific or not region specific, particularly because you as somebody who models could make the decision, okay, I think for simplicity we leave this as a non-region specific parameter, or we decide here we want to look at that and use it as a region specific parameter. Yeah. What also goes into this is that of course these models you can click together fairly quickly if you use the SPM interface. Whether they are then necessarily identifiable and all these parameters can actually be estimated from the data, I don't know whether that's necessarily clear. We will get back to this, hopefully then with a little bit of clearer notation. At this point, the important thing is the fifth and the fourth state variable of each region. So the hemodynamic states are used for predicting a single value. This is then for each region this Z value, and then of course these Z values are concatenated, downsampled, and then we get these time series. Yeah? Good, so that's kind of the meso level. Are there questions right now about the meso level? The meso level is mainly to structure a little bit the micro level, so that there's some preparation of what will happen now. Good. Then we can now go to actually the neuroscience of this whole model business, and go basically starting to talk about the evolution and observation functions in more detail. And we start with the neural state dynamics, which is usually also the only thing that you encounter when people talk about DCM. So although a big part of DCM for FMI is actually this hemodynamic balloon model, and as you see, it's actually 4/5 of each region's state variables are hemodynamic variable. It's not that much talked about, strangely. Although it's interesting because it's a biological, biophysical model. One of the reasons why there's maybe not that much talked about is that this was adapted from earlier work by the SPM developers. So Karl in 2003, and then later on Klaus and Stefan, who did some stuff in DCM for FMI. And of course, that's in a way not their invention. And they, of course, when they communicate and talk about this, they focus on their invention, which makes some sense. But then it gets a little bit forgotten that they built their invention on something that was there, which is also important to keep in mind when you actually use these models. But for now, we focus on their invention, namely the neural state dynamics. And hope everybody's happy. We start now with the neural state dynamics. And to get into the neural state dynamics, what is actually done, and this is also what you find in a lot of the documentation about DCM for FMI and also the implementation. So if you talk about the implementation of DCM for FMI for users who don't want to get their hands dirty in programming, there's a graphical user interface where you can click on things and you can specify what is known in the DCM world as the A, B, and C matrices. And you can specify the entries, or let's say what you actually specify are the priors for the parameters in these matrices. But you can specify these by clicking on matrix entries. And this is what most people then usually see, what you find in the SPM manual on DCM. So this is kind of the conventional description. What you need to do that is that you concatenate the neural state variables over regions in one neural state vector. And this is what I'm doing here right now. So we've learned that each region that is here denoted by this superscript, that's the region index. That for each of these regions, for each of these regions, the first neural state, the first state variable is the neural state. Yeah. So if we look into the second region and again take the neural state, and then we look into the third region and again take the neural state up to the nth, or in the old days M, region, and concatenate all of those, then we have a number of region dimensional vector of neural state variables. Yeah? So then we have a neural state vector, and each of these entries means the neural state in one of the regions. Now, from what I have presented on the overall state evolution, we can of course focus on the evolution of only the neural states, which we want to do now, and we can specify then for this neural state vector an evolution function that just follows from looking at these for all regions. Yeah? And this is what we are looking at. So I call this evolution function here then phi, maybe even phi f. Let's call it phi for now. This only talks about the evolution of the neural states, but over all regions. Yeah? Whereas what we've seen here talked about this talks about the evolution of the neural state in one region, however influenced by all other regions, and it talks about it in general terms, so it talks about it for the ith region, so it also talks about all regions, but one can of course focus only on the neural state. As we're doing here, and then we can think of in terms of a pure neural state evolution function and specify a neural system evolution. Yeah? So the idea of focusing on the pure neural system evolution, of course, behind that is the idea is that if we observe MR signals from different brain areas, then the interactions between these regions happen at the neural level and might be influenced by some cognitive factors or some input factors in our U functions. And once, or at a given time point, this means that the neural system over these regions attains a certain state, and then in a second region-specific thing, this is translated in via the neurovascular coupling to and the MR imaging process to an MR process. Yeah, so what we've also seen here, and this relates back to this, is that each regional state is influenced, or let's say for each region, the 4 hemodynamic state variables are influenced only by the neural state in that region. Yeah? That means neural states in other regions don't influence the bold signal or the MR signal in one region. It's only that the neural states are coupled, and then the neural state in one region is transferred into the bold signal in one region. What's the question? That's a question.
Yeah, I thought we learned last semester that this was one basic assumption.
What?
That different states or different conditions would not influence each other or something?
What?
After we think about
different conditions will not influence each other?
There was one basic assumption that different regions would not influence each other, but the name of the processes. Yeah, I think these are
cognitive processes?
Yes, the cognitive subtraction, like the basic assumption, I think.
Yes, it was this.
You add a cognitive one.
Yeah, that's a good, it's an interesting point to bring up. This has nothing to do with cognitive processes. Okay. I know where you said it, because I said you have a cognitive process here that influences this system. Yeah, this is why you thought of cognitive process. Okay, that makes sense, and that makes sense. If we relate it back to that, no, it's actually a good point. The thing is, so if one relates it back to that, it holds here in the way that if our U are actually cognitive processes. They don't influence each other. Yeah. So this cognitive process does not influence that, but the result that you get might actually, in terms of the MR signal, relate to interactions between cognitive processes. But try really not to think about this at this point, because this has nothing to do with cognitive stuff. So at this point, so I just think of the use as stimuli that drive the system at this point, and don't the whole thing, and this is really important. The whole thing does not want to do. It's a very weird approach to do neurocognitive modeling. It's biophysical modeling. Yeah. So don't think about in terms of psychology, in terms of cognition. This is biophysical modeling. This is about you drive the system, and then there are biological quantities in there, like neural states and hemodynamic variables, and then you get an R signal. This has nothing to do with solving cognitive problems. Yeah.
My question is if the hemodynamic states can influence each other if the regions of interest are very close?
No.
Yeah, no. That was just my question, if they can influence each other, because I was thinking of like when you have a hemodynamic response in one region, and also last semester we had this one slide where you talked about how what's called the bowl signal, how it kind of travels, like if you excite one side, travels also.
Yeah, that's not in. So of course, this is if you want, this is a biological fact, maybe even, but this is not modeled here. So if you in terms of if you use and you can only use SPM to do this kind of modeling, or you implement it yourself. And if you implement it yourself, you can build in something like that. If you use DCM, if you use SPM for that, and you decide that you have two regions of interest which are quite close together, what SPM will create are these 4 hemodynamic state variables for each region, and they will follow these equations and will not influence each other. Yeah? So these are the equations that are always assumed in the DCM5MI framework in SPM. But of course, you're right that this might be, especially if you're really close together, but then you would have to change the equations so that this is reflected. Yeah? And this is also why this is actually a good question in terms of motivating what I'm doing here, because I'm trying to show you like the details, and if you're not happy with the details, then you should not say, this is a bad approach, I don't want, I want to do classification now. What you should do is, well, this is biologically interesting, but it's not quite there. Maybe I can improve on it. And then you improve on it. Yeah?
Is it common that people
improve on it? No. No, the only people who improve on it are, of course, the London people. So essentially, the only people who did there are like 2 or 3 other people who actually went a little bit into the whole thing. But if the much more common thing is that there's a new paper by the Phil or Wellcome Trust Group, Wellcome Trust Imaging Center Group, that proposes some modification of this. Reason for that is, of course, that they try to keep many secret what's actually going on. So it's needs quite some time to get into it and to be able to actually modify something sensibly. The other thing is that, of course, even if it's more or less clearly laid out, it still requires work to get into it, and of course it requires less work to click things around in SPM and just have something happening that you don't understand.
Would you then work in the SPM functions and modify them, or would you build your whole framework out of such a...
Well, that's what you need to decide. That depends on which level you work. So, for example, for DCM for EEG, I was not quite happy with the inversion routines that DCM for EEG uses, and I wanted to modify some parts there. But I didn't want to modify at that point the neural population models. So I used the code for the neural population models that they use, but changed other code. Good, but then let's return to the neural state evolution and maybe I mean, this question about the cognitive and neuro side of things, that's very interesting, but that's a very hard question. So my plan, so I'm currently working a lot on cognitive modeling. So basically, in terms of MAR levels at the computational algorithmic level, I've worked on this, and my plan for the next 10 years is to bring these two closer together. So, but this would be then going into this direction to, relate cognitive intuitions that are sometimes cast in a good way in algorithmic models, and bring them closer to the biophysical side. Good, but now let's continue with the neural state stuff, if there are no questions, but these were interesting discussions. So the neural state evolution. So we now extracted essentially from each region of interest, we extracted the neural state variable and concatenated them in a vector, which we call x1, and because the neural state variables have evolution functions in this overall evolution function of this modeling framework. Also, if we look at the extracted versions now concatenated, they have an evolution function. Actually, this evolution function might even look a little bit simpler compared to what we've seen previously. It looks as follows. So this phi function takes an nr dimensional vector, because we only have one neural state variable per region. So let's say we have, like here, 3 regions 1, 2, 3. Then we have a 3-dimensional vector. Our input function, so still there are NC conditions, and we only, and this is why I put a 1 here, we only need a subset or subspace of this parameter space for the evolution function, because we only need the neural parameters, right? So we don't need these kappa tau and stuff that relate to the hemodynamic parameters. We only need essentially these parameters that are in the first that are applied to the first state of each region, which are these A's, B's, and C's. A, B, and C's. Now this function here takes the following form, and this is in a way that's the famous DCM function that you will find when people talk about DCM, as I said. It looks as follows. AX1 plus UK BK x1 plus CU, and this is K and C. So, good. So what do we have here? X1 is our state vector. Again, this is a vector that has as many entries as there are number of regions. Again, keep in mind this is time dependent. So this x1 is the neural state vector at time t. The parameters A, B, and C are not time dependent. Yeah, none of the parameters, in fact, and this is why they are called parameters, are time dependent. Yeah. So x1 is time dependent, U is time dependent, but A and B and C are not time dependent. What is A? A is a matrix which is a square in the number of regions. And what it specifies is the influence that each of the state variables has on the rate of change of each of the state variables. So maybe to get started, we only look at that in a little bit more detail. So if we would think there would only be the AX1 term, then our system would look like this. Yeah. If we write this out for let's say 3 regions, we would have the null state of the first region, the null state of the second region, null state of the third region. The rate of change of these is given by the matrix R times their current states. Yeah, that means the null states. Oh, so, yeah, no, that's fine. It's just a little bit. Maybe I should do that a little bit different, because otherwise you get confused. I should not do it a little bit different. I should do it as I said I would do it. So like this. Yeah. Just the index change. So again, this is the first state of each region. The region is indexed by the superscript, so the bracketed superscript 1, 2, 3, and it's the first state variable in each of these regions. Now, the rate of change of each of these state variables is influenced by the current state in each of these regions. Yeah, so the different null state variables can influence the rate of change in the different regions, multiplied by this matrix R, and this matrix R has parameters and maybe we do that. That may be a good exercise, also with respect to the equation above. This is a 3-dimensional vector, so what we get for the rate of change of each region's null state variable is, if we call this J, for the first one, for the second one, and for the third one. No, it's better. Yeah. So look again what this means. This is the rate of change of the null state variable in the first region. It is given by the weighted sum of the null states in all J regions, and the weighting is done by parameters A1J, so these 3 parameters, A11, A12, and A13. A11 specifies how the null state in a region itself influences it. For the first null state, A12 specifies how the null state in the second region influences the rate of change in the null state of the first region, and A13 specifies how the neural state in the third region, of course always at time point t, influences the rate of change of the neural state in the first region. That's only for the A. Let's just compare this to what we've written above. So this is what we've just wrote down. This is this. Yeah. So I ignored for now, as you see, obviously I ignored the B and the C and just wrote this out. Yeah, we will look at examples. Are these? Yeah, but to look at the examples, we also need to look at the C. So let's look at the C first, and then we look at an example. So these parameters here, yeah. So the parameters in this A matrix, they are what is referred to as baseline connectivity or resting connectivity, or whatever parameters in DCM. The important thing is that this is independent of the conditions, the condition functions. Yeah. So this is just a dynamical system that has certain parameters. Certain state variables influence the rate of change of other state variables. Whether they increase the rate of change or decrease the rate of change, that depends on the sign of the parameter. How strong they do depends on the sign of the parameter. If the parameter is 0, they don't have any influence. All these things are encoded in the function. And already these kind of systems actually have very rich repertoires, dynamical repertoires. So if you do a course in dynamical systems theory, this is a typical thing where you start off with, and then depending on the properties of these parameters, essentially the determinant and the trace of this matrix A, you can have different kind of behaviors of such a neural system. So you can have oscillations, you can have I would call them explosions, so that they just get larger and larger. You can have these kind of, they have all names that I don't come up with. You can have these spirals, inward spirals. So they already, depending on the parameters, have quite a rich dynamical repertoire, even in this very basic setting. Maybe one thing that is interesting here, of course, this is instantaneous, so that means that the rate of change, that the state of the neural state variable in region 2 at time t influences the rate of change in region 1 instantaneously. Yeah, so at time, let's say 2 seconds, this has a state of 5. Then it affects at time 2 seconds the rate of change of the other region with at this point in time. Yeah, so there's no conduction delay between regions.
Would we assume that these A parameters are fixed? Like if we look at the same regions of interest, for example, I don't know, I do 2 experiments, I don't know, and I have the same 3 regions of interest, they should be connected in the same way, right?
Yeah, that's a good point. So the question is, in a way, is this structural connectivity? So is this like DTI? So is this actually axon bundles? And does it reflect that? That's always what they try to hope. It's not. So it's not structural connectivity. In a way, I would agree with you. It should. So, for example, if this is the resting connectivity between V1 and parietal cortex, it should be independent of whether you do a perceptual decision-making experiment or you do a social inference experiment or something like that. I would say this question is an interesting research project. So I think this has not been systematically investigated at all. Yeah? People could argue in a way, one can argue also that this is not the case, but to say this is kind of the resting, or that this is the connectivity structure that the system adheres to if you do a certain task. Can also argue like that. If
theoretical driven, like I implement parameters that I think fit for my theory.
yeah, so yes, so in the so we are not there, of course, at all. But in terms of how these parameters are estimated or not estimated, is that in general, the parameters of the A matrix have very tight priors. That means they have fixed parameters. So the A matrix is usually fixed by the user, reflecting certain connectivities. What then happens, in fact, is that users assume different connectivity schemes and look which one's best, which then also means that there's some kind of meta level parameter estimation. And of course, again, one would assume, like what you suggested, that if this is really reflecting some kind of structural connectivity, that this is the same or identical over experiments. Yeah. Yeah. Good, then let me, in the last 5 minutes at least, introduce the C parameter, and then we can start next time by looking at an example which only has A and C parameters, and then talk about the B stuff later. So here, this... Oh, sorry.
So it's actually a very connected question. So when we're talking about A matrices, the assumption is that it's at, for example, time 0. Then after the condition is introduced, does it fall back to the same A matrices when the configuration?
No, the A matrix is not time dependent. So the A matrix is, and these parameters, so A matrix is just a set of parameters. These are constant throughout the entire modeling initiative. They never change.
So irrespective of when the condition is introduced, we'll always use the same thing.
The conditions enter the whole thing in this UK-BK term. And we will talk about that. Yeah, we haven't talked about yet. So far, we have not addressed how the different experimental conditions affect this. Yeah? One basic thing, how the experimental conditions affect this, is actually this term CU. So let's briefly look at that, because that's relatively quickly. So if only this CU term would be there, then we would have that the rate of change of x is given by C times U. U, remember, and especially UT, that's an n condition or events or cognitive processes, but I'm not saying that, vector. So this matrix C needs to be number of regions times number of conditions, because you need a number of region vector coming out of that, and it needs to be multiplied with a number of condition vector. So let's say again that we have 3 regions, then we have 3 neural state variables, and the rate of change, if we only had the CU, or let's say the R matrix would be all zeros, then of course you have the same thing, and the B matrices, which we haven't talked about at all, will also be all zeros. Then we would multiply here a matrix that looks like this. With so let's just define it. So that's three regions, 2 conditions. houses and faces, times u1, u2. Yeah. Remember that these functions here are stick functions. So let's say u1 looks like this, and u2 kind of orthogonal to that. So whenever, so this is time here. So u2 is on when u1 is not on. If one then computes this, this would of course go k from 1 to number of conditions, c c1 k u k c2 k u k and c3k uk. So what this then of course specifies is how the state of the input function affects the rate of change of each of the neural state variables, and depending on some parameter. So if the parameter is 0, then the input function does not affect the rate of change in this term of the neural state vector. If it's non-zero, then it affects it. Typical use of this is that these are visual stimuli. One of these regions is a visual region. Then the parameters that people specify for this visual region are then, let's say, 1. So let's say this is here V1, and this is IPS, and this is DLPFC. Then people would do something like this, 1, 1. So the visual stimuli affect V1, but they don't directly affect IPS and DLPFC. Yeah. Let's have a look whether we actually specified this correct up here. CI, yes, K, UK, number of conditions. Yeah. So this is this term, and we've now basically talked about this one, and we talked about this one. We haven't talked about the one in the middle. This is the C matrix, is also called the input parameter matrix. And again, this is not dependent on conditions or time, so C is simply fixed. One again would assume that this is over different experiments that's identical. Yeah. One important thing is that this renders the whole system non-autonomous. Yeah. So we looked at things like this before, but there is nothing that varies as a function of time independent of the system. Yeah. X1 is a vector that is of course depending on this whole system, but it's not some independent function of time. The U is an independent function of time, so it sometimes puts in some, affects the rate of state, the rate of change of a state, and sometimes it doesn't, which renders the whole thing what is called non-autonomous. Good, so I think I want to stop here, because then we can look at the example that is in 43.2, this figure, as the first thing next time, and then in a second step talk about the B matrices. Yeah? Good. Then let's stop here, have a break, and then continue at briefly after 10 with programming.